Okay, so in this first passage, we're looking at a classic competition graph. So what you can see here is each of these two species were grown in the same environment, and their density curves are quite different. The species exhibited by the green line actually becomes excluded, and this is called competitive exclusion, when one of your species is able to outcompete the other. Now, when the green species was then grown with the orange species, you can obviously see that they were able to coexist. So in the first situation, this is what we call competitive exclusion. One of those species become extinct. And in this situation here, something else happened that allowed them to coexist. It could have been a matter of differentiating what they ate or their resources in some way. So the question 19, was referring to which of the students in the previous page was describing a symbiotic relationship as a reason for the graph. In other words, why does this graph here look as such? So if you turn to the other page, you will see that only one of the students, student 1, referred to any other organism other than the paramecium, which were depicted in the two previous graphs. So here's the photosynthetic algae called chlorella that they referenced. Therefore, only student 1 described that symbiotic relationship. The next passage of interest deals with electrophoresis. In particular, we are separating amino acids by certain properties. So here you have a basic structure of an amino acid. Some amino acids are polar, some are nonpolar, some are charged, some are uncharged. Okay, so in this particular question, they are looking at taking a paper strip which is soaked in a solution of a particular pH. Those pHs varied from 10, 9, 6, 5.5, and 4.5. And so you basically take your amino acid and you put it in the middle. And then pHs have a tendency to alter those properties of those amino acids. So for example, you can see, according to the data here, when the pH was 10, your amino acid actually migrated towards the positive end. It would have done that because it was negatively charged. pH of 9, it still migrated towards the positive end, but not as much. And then at pH of 6, notice it doesn't move at all. The reason for that is because at certain pHs, the amino acid will pretty much lose its charge. The pH will negate its charge, and we call that the isoelectric point, which is described in this paragraph right here. So the question we're going to look at deals with what is the isoelectric point of leucine? So again, referring back to that data, when I had my pH equals 6, my amino acids never left this position right here, so they became uncharged. Therefore, there was no migration this way, and there was no migration this way. So I know that the pH is 6, and that would be my isoelectric point. All right. Next question deals with spring constants, also referred to as Hooke's law. So basically what we have here is a scenario. We're going to take we're going to apply a certain force and see how much it displaces a spring. In other words, how much it compresses it. And so we generally get a relationship where we apply a force and we get a certain displacement. We apply a greater force, we get more displacement. We apply our greater force, we get more displacement, and so on and so forth. When we show our trend line, we have F, change in F per change in X, or displacement, equals the slope, which in this case is a value of K. And K is considered a spring constant. Obviously, some springs are more stiff than others, so their spring constants vary. So in our scenario here, we are looking at firing a projectile with a particular velocity at a block which is attached to our spring here. So again, the spring will have a K value, the block will have some mass, the velocity of the projectile is included, and this projectile will obviously have a mass as well. Okay. One of the first questions deals with determining how many different test items you have. Okay, so if you go back and look at the table, we are testing 12 different items. We have a projectile with a mass of 0.01 that has a velocity of 5. We have a projectile 0.02 with a velocity of 5. We have a projectile 0.03 kilograms and a velocity of 5. We have a projectile 0.01, but now the velocity is 10. A projectile 0.01 kilograms and a velocity of 15. And a 0.01 kilograms and a velocity of 20. So that's 6 so far. Then we come down here, we have a 1 kilogram block, and we have a spring constant with the spring attached to that block of 3. We have a 2 kilogram block, spring constant 3, a 3 kilogram block and a spring constant 3, a 1 kilogram block and a spring constant 5, 1 kilogram block, 7 is my spring constant here. I got a 1 kilogram block and a K value of 9. So you can see that's going to give me 12 total different test items here. So on question 28, we're looking at correct answer of G. Okay, 32 basically asked you to summarize the results of both studies, and they want to give you a combination that would yield the greatest value of K. All right, so back to the diagram. A value of X. We're looking at the greatest value of X. So again, remember that X is my displacement of my block, which is attached to my spring. So it's extremely similar to my displacement on the spring, which was labeled down here. Okay? In order to get the greatest displacement, what we're looking for is a projectile with a fairly high mass, a projectile with a fairly high velocity. When it strikes the block, we want the block to have a low mass because that will make it easier to slide across my surface here. Even though it's no friction, it still would have inertia. And then we want a K value here that's extremely low, which means it's not stiff and will allow that block to slide. So if we look at our options, we can see that J has a projectile mass that's high, 0.03 compared to some of the others, but the velocity is 20 compared to 5. My block mass is low, and my K value is the lowest, it's 3.0. So all those variables would result in the greatest compression of the spring, which is basically the displacement of that block. Okay, and the last passage of interest here is going to be the one dealing with sucrose. We're hydrolyzing sucrose in the presence of an enzyme or a catalyst, and in the other experiment, in this particular passage, we are not using the catalyst. We're actually changing the pH, the buffer pH. Okay, so basic reaction here, we have, this is our disaccharide, our sucrose molecule, and we can see that it's going to yield a glucose molecule here, and then this is a fructose molecule here. The graph is showing the sucrose hydrolyzed or broken down over time. Now I'm only going to show one line here because the trend on all of them is the same. That is a linear line, which basically means my rate of hydrolyzation is constant. Okay, now that would also infer that I have a readily available supply of my reactant. I am not running low on this reactant whatsoever. So, as time proceeds, my sucrose being hydrolyzed is a constant rate. In other words, this slope here is constant. Okay? So all that being said, this first question that we're dealing with, question 35, during each of the trials of the experiment, the mass of sucrose that was hydrolyzed increased. That's true, they're just restating what we know here. The hydrolyzed sucrose is increasing. Therefore, the mass of the, or the concentration of the fructose, so go back over here to this diagram, this is my fructose right here, that's my 5-sided sugar. So if I'm constantly hydrolyzing this molecule and producing or yielding this molecule, then this will also increase. Okay, so in that question we're looking at the concentration of fructose increasing only. The only way that you would get the remaining constant for that sucrose is if your reactant ran low and it wasn't as readily available. So you might see something like the line will have this general pattern and then it'll actually plateau and level off, and so you're actually getting a changing slope here. Okay, so it's constant in the beginning. As my reactant becomes less available to that catalyst, my slope is decreasing, and then it actually goes to 0 because I no longer have any of my product. Okay, and then 38 is asking what is the same in every trial of experiment 2 but varies across the trials in experiment 1. So what was varied across experiment 1? So if I go back and look at what experiment 1 was varying, I can see this last sentence right here. I have 6 different imidazole concentration. Now this right here is my catalyst or my enzyme. This word imidazole, I believe is how you say that. So that is varying for experiment number 1. That is different. I'm getting different concentrations of that. However, in experiment 2, I'm actually keeping the amount of that catalyst the same. Therefore, what was varied across the trials for experiment 1 but kept same for trial 2, that's going to have to be this concentration of the catalyst. So that's going to be answer J.